In today's lesson, we are going to talk about linear homogeneous differential equations with constant coefficients. Here is a little introduction. Differential equations describes how quantities change and are widely used in mathematics, physics, and engineering. And one of the most important and structured types is the class of linear homogeneous differential equations with constant coefficients. These equations are important because they are easy to solve and using a systematic method and appear in many real-world applications and have well-structured and predictable solutions. Let's look at the general form. The general form of an nth-order linear differential equation is can be written as this one. Let's look at some basic concepts. We have here the words linear, constant coefficients, and homogeneous. First, we have the linearity. The equation is linear if y and its derivatives appear only to the first power. For example, y prime plus xy is equal to 0. This equation is called linear, but this one plus xy squared is equal to 0 is not linear because the second order we have here, the y to the power of 2, and the second one is the homogeneous. The equation is called homogeneous because the right-hand side of the equation is 0. If it's not, which means that if it is equal to f of x, we call this equation non-homogeneous differential equation. And here, an from an to a0 are constant numbers. Let's look at the solving this equation. Main idea of the solution. To get the solution, we assume a solution of the form y is equal to e to the power of rx. This works because derivatives of exponential functions are proportional to the functions itself. So we substitute y into the equation and we can get the characteristic equation, which is n r to the power of n plus n minus 1 r to the power of n minus 1 plus 0 plus a0 is equal to 0. So, and we can get the roots of this equation, which are r1, r2, and etc. rn. And there are three cases. And case number 1, we can get the distinct real roots. If we have the distinct real roots, the solution of the linear homogeneous differential equation can be written as y equals 1 a r1x plus 2 e r2x plus etc. n e Rnx. For example, we are given this kind of equation, second order derivative of y is equal to 0. We can write from this equation the calculus equation, which is r squared plus r minus 6 is equal to 0. And we have the characteristic roots, which is the one of which is minus 3, and the second one is equal to 2. And we can see the characteristic roots are different and they are real. So we can write the solution as the form of y is equal to C1 e to the power of minus root x plus C2 e to the power of 2x. Solving the characteristic equation, we can get repeated roots. If a root r has multiplicity k, then the solution can be written as y is equal to C1 plus C2x plus 0 plus Cn x minus 1 and e to the power of rx. Let's look at one example. Plus 2 prime plus y is equal to 0. And from this equation, we can get the characteristic equation, which is r squared plus 2r plus 1 is equal to 0. And we have the repeated root, which is r is equal to minus 1. And using this, we can write the solution y is equal to C1 plus C2x and e to the power of minus x. And in the third case, we're going to have complex roots, which is r is equal to a plus minus b. Here, a is the real part of the complex number, and b is the imaginary part of the complex number. Then we can write the solution y is equal to e to the power of ax and C1 cosine bx plus C2 sine bx. For example, y plus 4 y prime plus 5y is equal to 0. And we have the characteristic equation r squared plus 4r plus 5 is equal to 0. And we can have the complex characteristic root, which is r is equal to minus 2 plus minus I. And the real part here is minus 2, and the imaginary part of the complex number is 1. So using this, we can write the solution y is equal to e to the power of minus 2x c1 cosine x plus c2 sine x. And this is the solution of this